Hello again. So you can probably tell where this is going, but let me just continue walking along the steps. As I mentioned last two lectures, I'm interested particularly in the case of Boolean formulas that are unsatisfiable and for which we want to produce a checkable proof of unsatisfiability. Last time I covered CDCL, which as I mentioned is the best general purpose known technique for satisfiability solvers that generates very natural proofs in standard resolution for which there's a very powerful infrastructure for proof checking. And so that whole framework is very well developed. But we also saw that CDCL solvers and resolution in general have some weaknesses, that there's some problems which are inherently exponential, even though we can, from looking at them at a higher level, see that these are clearly unsatisfiable formulas. So today I'm going to introduce binary decision diagrams. And the reason I'm doing this is, as we'll see in the next lecture, there's a very natural way to encode the steps of a BDD algorithm into proof steps in extended resolution and be able to get very efficient solutions for some of the problems that CDCL does poorly with. But for today, we're not going to worry about proofs. We're just going to worry about Boolean manipulation. So BDDs are an idea that I came up with many, many years ago when I was a young assistant professor. And it was an idea of representing a Boolean function in a graph that built on some work that had been done by others before. And what I did was I put a particular restriction on it, known as ordered binary decision diagrams, and came up with a whole family of algorithms for constructing these, manipulating them, operating on them, and showing that they were, in practice, very useful data structures. So you can think of, I went from some abstract representation of Boolean functions to a data structure with an associated set of algorithms. These have found use in many different contexts, including Boolean satisfiability, but also areas such as model checking and other areas beyond just pure Boolean satisfiability. And the main idea that differentiates it from standard SAT is it's more of a bottom-up approach, meaning I start with a low-level representation and build up more complex ones. Whereas CDCL you can think of as a top-down. You're given a collection of clauses and you start searching for ways to satisfy those clauses from the top down. So let's go back to some basics. We know that we can represent any Boolean function as a truth table, and a truth table can readily be converted into a tree where, in this case, the nodes represent the Boolean variables, and each Boolean variable can be assigned either 1, which I'll show in red solid, or 0, which I'll show green dashed lines. So given an assignment, say 1, 0, 1, we can trace a path in this tree and come to a leaf, a terminal node, that's labeled either 1 or 0, and say that's the value of this function for this particular assignment. So this is all pretty straightforward. But now what we can do is take this tree and create a more compressed form by using some very simple transformations. So in particular, we'll notice that there's really only two different leaf values, so why have a bunch of leaf nodes when we can just have two? And now you'll see examples, for example here, where regardless of whether x3 is 0 or 1, this function is going to yield a 0. So I can just get rid of those, that test there. And here you'll see two examples where it's labeled by the variable x3 and the outcomes are the same in either case. So why not just make one unique copy of that node and have multiple pointers to it? And if we apply those kind of rules to variable 3, we'll get this reduced form. And now you can see, oh, I can apply that same rule here at x2 and keep doing this upward in the graph. until I can no longer apply either of these two simplification rules. And that is, right there, a ordered binary decision diagram, a reduced ordered binary decision diagram. And you can see the ordering rule is that I'm requiring that the testing of variables along any path be according to some unique ordering of the variables. And so I'll just call it a BDD for simplification, but assume that I always mean reduced and ordered binary decision diagrams. So one interesting property of this is if we could create a set of clauses and somehow convert them to a BDD, we can very clearly determine whether or not that formula is satisfiable. In particular, there's only one way to represent the BDD for an unsatisfiable formula. That's the leaf with value 0. I'll use the bottom symbol for that. It's unique. Now, of course, the problem is that going from CNF to BDD might require an exponential step. So I haven't really solved P versus NP. I've just shown that there's a different representation for which whether it's satisfiable or unsatisfiable becomes a trivial test. One other feature of BDDs, which is either good or bad depending on how you think about it, is that the ordering of variables can be quite critical into how large the BDD representation is. So you'll see here I have two different ways of ordering the variables A1, 2, 3, B1, 2, 3. And in one case, I'll get a linear growth in the representation, and another in the exponential. And the way to think about this is if I do it in this paired way, then as I go through the variables in sequence, A1 then B1, well, if both of those are 1, then the function is a 1, and otherwise, it will only depend on the assignments to A2 and so forth. And so I have this sort of linear sequence of tests. Whereas if I have to look only first at all the A variables before any of the B variables occur in this graph, I essentially have to encode as a tree all the 8, in this case, or in general 2 to the n possible combinations of the variables A1 through A sub n. So there's been a lot of work over the years in various heuristic methods to find orderings. And I won't talk about that too much, but it's an interesting topic in its own right. One good case, though, are parity constraints. You can see that an odd parity is just a series of tests where along the right-hand branch are the cases where I have odd parity, and along the left-hand branch are cases where I have even parity. And so in the end, since this is an odd parity test, I want a 1 along the right-hand branch. The even parity is the same representation, just with the two leaves reversed. And in general, the negation of a function can be obtained by just flipping the values of the two leaves. So this is absolutely independent of the variable ordering. So this is a real strength of BDDs. And as we saw, CDCL has a problem. It takes an exponential number of clauses just to express it. And we also showed examples that Chu-Hurley benchmark for which the CDCL does very poorly. So somehow in here might be a chance to do well with parity constraints. And those can be a very important class of problems in practice. So as I mentioned, a BDD is not just a representation, it's a data structure with associated algorithms. And the general strategy we follow is, as I mentioned, a bottom-up one, that we keep generating new BDDs and using those BDDs to generate more BDDs, building up from the bottom up to create an overall representation of a Boolean formula. And in each step, we have these operations that take BDDs as arguments and produce BDDs as results. And we'll assume in general they'll all use the same variable ordering. So the most important general algorithm is what is called the apply algorithm, which is given the BDD representations of two functions, here I call it f and g, and some Boolean operator, imagine and, or exclusive or. And I want to create the Boolean function h, which represents the function u to be obtained by composing these two argument functions with this Boolean operation. So for example, for the case of or disjunction, I'd end up with, my goal is to create a BDD like this, representing the or of functions f and g. And the algorithm for doing this is a fairly natural recursive algorithm that begins by traversing, according to a depth-first traversal, the two arguments graphs and keeping with that progression until you hit terminal cases. And then as that continues back up, it produces the BDD representation of the result. So let me just demonstrate here using a graph to represent the series of recursive calls. So I start at the top level. My two arguments are f and g, represented by these BDD nodes, capital F1 and capital G1. And I'll say, well, now variable a can be either 0 or 1, so let me split on those two cases. And for the case of a equals 0, you'd get f2 over here and g2 for the second argument. And similarly for, we'd continue that recursion at step first. We'd say, well, now between f2 and g2, one is based on variable b and the other is variable d. But I'll take the one that comes first in the ordering. So I'll split on variable b in this case. And b assigned 0 gives me f3, and I still have g2 I'm passing along as my second argument. And that will be a terminal case. It's just the or of f3 and g2. And in fact, those are identical. So the result of that will just be the node with value d. It will just be another copy of that node. And I come back to the recursion, and at this point I say, okay, I already did b equals 0, now let's do b equals 1, and so forth. You get the general idea that in general we're walking through the two arguments, always branching on the topmost variable of the pair. And at the end, if you trace all the recursive calls, you'll have built up a representation that looks like this. And if we just take that, and that is, in fact, a BDD of sorts. It's just not reduced. So if we reduce that back, we'll get our target result, this function h, representing the or of those two argument functions as a BDD. So that is this core algorithm, the apply algorithm. So how can we apply this with a SAT solver? Well, the most obvious sort of brute force technique is say, well, each clause is the or of a set of literals. I can build up a BDDs out of ors because I know how to apply the function or to some subfunctions, including ones representing the individual literals. And similarly, at the top level, I can form the conjunction of the BDDs representing all the input clauses. And I can imagine either being not naive and just doing them in succession or trying to create some tree of conjunctions to combine them all together. But in any case, I'm going to end up with either a BDD representing that unique unsatisfiable function, which is just a single leaf, or some other BDD that will say, well, in general, there can be one or more solutions here. And in fact, what I've effectively done is created a BDD representation of all possible satisfying solutions to that formula. So the good news is it's not just a SAT solver, it's an all SAT solver. It finds all possible solutions. The bad news is, well, that's way overkill for most of my applications. And in fact, it's not going to work very well in general for big formulas. It's just way too complex. And indeed, if I apply that to my Chu-Holy parity benchmark, though, trying to compare the even and odd parity where one of the cases are permuted randomly, it does very poorly. It does even worse than Keysat. So it's not just an exponential algorithm, but it's a really bad exponential algorithm. And I found within my time limit of 600 seconds, I could only get up to n equals 24. So here's an approach that sometimes works, not always, but it can be much better. That's called bucket elimination or bucket evaluation. And the general scheme is I'm going to order my BDDs by what their root variable is. And what I'll do is at each step, I'll take the one that's in the topmost bucket and I'll form their conjunction just like I did before. And typically that will be a Boolean function then that depends on that variable. But now this will be the only case where I have that particular variable in any of my BDDs that I'm representing. So I can safely existentially quantify it, and that will create a BDD with that depends on some lower variable in the ordering. Sounds a little complicated, but it's a pretty straightforward idea that I'll demonstrate to you. So again, just to say that what I just said in words, in pseudocode, I'm going to create a BDD representation of each clause, and then I'll assign it to the bucket, which is just a list, of according to its root variable. And now I'll go through each bucket, starting with the highest one in the ordering, which will be actually the least numbered one, to the lowest one in the ordering, so that the and each step I'll form the conjunction of all the BDDs in that bucket. If I hit an unsat case, then I can declare the formula to be unsatisfiable. Otherwise, I'll do the existential quantification. And in this case, existential quantification is just taking the two children and forming their disjunction. And then I'll assign that result to appropriate bucket depending on its root variable. And if I can get all the way to the end, then I guarantee, actually, if I get all the way to the end, I'll just have the leaf representing the formula, the Boolean case of true, because I've eliminated all the variables along the way. So let me just show you as an example using the an example formula. It's different from the ones I was using before. But here, imagine we have 5 clauses, as I've shown here, and we assign them to an ordering, buckets, according to the first A, B, or C variable that occurs in that. So there'll be 2 in bucket A, 2 in bucket B, and 1 in bucket C. And I'll start with bucket A, the highest up in the ordering. And I'll form their conjunction. In this case, it's not a clause anymore. You can think of it as a function that is just the if then else splitting on variable A, giving me either B or C bar. But that's now the single unique BDD here that contains any reference to variable A. So I can existentially quantify it, which is actually just compute the OR of its 2 children. And that OR will be a function that no longer depends on A. In this case, it will depend on B and C. And in fact, it can be shown to be either B or C. And that now will become part of bucket B. So if I form the conjunction of the BDDs that are in bucket B, that will turn out to be equivalent to the Boolean formula B and C. And now I do the existential quantification of that, which is, again, just the OR of the 2 children here. One is 0 and the other is C, and so their disjunction will just be C. And so now in my bucket, I have the BDD representation of C and the BDD representation of not C, and their conjunction is false. And so I've come up with the unique leaf. So you can see here that I've taken these clauses, and by this sequence of conjunctions and quantification steps, I've reduced it to a representation of the unsatisfiable formula. By the way, if the formula were satisfied, I'd end up with the leaf 1, and I could work my way backward through those bucket eliminations and generate a satisfying solution. But we're only doing unsat in these lectures. So if I put that into a BDD-based SAT solver that I've created called TB-SAT, I showed you before the results of direct, and it did very poorly. But now for bucket elimination, you'll see all of a sudden I can do very well. I can, it takes me just a little more than 600 seconds to do the case of n equals 10,000. So consider the advantage I've gotten. I went from 42 with KeySought. I went back to 24 with direct evaluation. And now I've jumped ahead to almost 10,000 within a 600-second time limit. So I'm orders of magnitude more efficient. And it's a little unclear what this curve is, but it's polynomial in n. So I've clearly somehow gone a major step beyond the capabilities of what CDCL can give you. As I mentioned, it has a lot to do with the fact that parity constraints can be represented very efficiently using BDDs. And the difference between these two is, back here, I was having to keep track of the assignments to all the encoding variables as I went along. And with bucket elimination, that existential quantification lets me forget about a lot of the low-level details of what the parity is, and just keep track of what are my top-level constraints, so that at the end, it's a very simple comparison of even versus odd parity. So what this shows you is that there is something about BDDs that's special compared to CDCL. But what it doesn't show you is, how do I generate proofs when I do these BDD operations? And so that's the step that I need to do next, is somehow go from BDD to proof generation.